For every equilibrium reaction, you will have the value of K, or the equilibrium constant. In this case, we have two different reactions, and the first reaction has the equilibrium constant of K1, and the second one has equilibrium constant of K2. If we to add up this reaction, then we have to multiply the K. So K1 multiplied by K2. Now in the case if we want to cancel out C, we have to multiply the first reaction by 2, so it becomes 4A, 2B, and 2C. So now we can cancel out the 2C. Now if we multiply the reaction by 2, then we have to take the K1 squared. So now the total for the reaction will become like this. And the K for this reaction, or let's call it K3, it will be equal to K1 squared multiplied by K2. So the general rule is that if you add reactions, you multiply the K. So on. If you multiply the reaction by a certain number of n, then you have to take that equilibrium constant and power it to the nth value. For instance, if you divide the reaction by 2, that means you are multiplying it by a half. Therefore, the new K will be equal to the square roots of K1, or K1 power to the half. Next, we will discuss what is called as the Le Chatelier's principle, which is the shifting of the equilibrium to maintain the equilibrium condition. So first up is the addition or removal of either the reactant or the product. The principle is if something is removed, then the equilibrium will shift towards that removed species. So for instance, if we take A, the equilibrium will shift to the left. If we take A, the equilibrium will shift to the left. And if we take B, the equilibrium will shift to the right. Also, if we add some A, then the equilibrium will shift to the right. If we add some B, then the equilibrium will shift to the left. Something that is removed will cause the equilibrium moved towards its side, and something that is being added will cause the equilibrium to move toward the other side to maintain, again, the equilibrium condition. Now, the next thing is changing in volume or pressure, and this is normally very prominent if you have gaseous reaction like this. When the volume of the container expands, the reaction will allow forming of more gases, and therefore, if the volume goes up, the reaction will shift toward the one with more gas. And pressure normally is the inverse of the volume, meaning that if this reaction, we increase the volume, that means the reaction will shift to the right towards the one with more gas, because here you have two gases or two molecules of gas, and here we only have one gas of A. Increasing the volume means that we are decreasing the pressure. So if we decrease the pressure, and what happens is that the reaction will shift also towards the right side. So again, if we increase the volume, the reaction will shift toward the one with more gas. And increasing the volume means that we are lowering the pressure. So volume and pressure, they are highly dependent on each other. And of course, the opposite would be if we to add the pressure, that means we decrease the volume, and the reaction or the equilibrium will shift towards less gas, so it will shift towards the A side. Another parameter is change in temperature. For change in temperature, we have to write down the thermochemical equation. So not only the chemical equation like this, we also need to know the delta H of this reaction. Now, if we have an endothermic reaction, we can see that the delta H is positive value. This is endothermic. In this case, if we change the temperature, if the temperature goes up, for endothermic reaction, the equilibrium will shift toward the product. Because you can imagine for endothermic reaction like this, the Q is over here because it receives some energy in the form of heat. So if we add the temperature, we are adding Q into the system, so it will shift the equilibrium towards the other side, towards the product. On the other hand, if we have exothermic reaction, the Q is not going to be in the reactant side, but it's going to be at the product side. And therefore, if we increase the temperature, so if we add more heat, the reaction will shift toward the left side. So normally, you can remember that change for the temperature, the increase of the temperature or increasing heat in the system will shift toward the product for the endothermic reaction and the opposite for the exothermic reaction. And finally, addition of catalysts or addition of inert gases. These two aspects will not shift the equilibrium, will not cause any shifting to the equilibrium. For instance, the catalyst will just help the equilibrium to be reached faster, but it will not shift the equilibrium neither to the product side nor to the reactant side. And same goes for the addition of inert gases like helium, argon, neon. So the groups from noble gases, they will also not shift any of the equilibrium. Now we will discuss the thermodynamic aspect of the equilibrium. So before we have been introduced to this term of delta G equal to delta H minus to T delta S, where delta G is the Gibbs free energy, delta H is the enthalpy, and delta S is the entropy. Now we have another equation for delta G and K, and delta G is equal to minus RT ln K, where K is of course the constant of equilibrium or equilibrium constant. R is the ideal gas constant, which is 8.314 joule over Kelvin mole, and T is temperature in Kelvin. If we to combine these two equations, so delta H minus T delta S is equal to minus RT ln K. And we can change this form into this one, where ln K is equal to minus delta H over RT plus delta S over R. Now, the idea here is for us to find the new K. As I mentioned, the only thing that would change the K is the new value of temperature. So if T1 corresponds to K1 and T2 corresponds to K2, we can find a mathematical equations that connect them. Now, do not confuse the capital K with the not capital K. The non-capital K is the rate constant that we discuss in the kinetic chapters. The capital K is the equilibrium constant that we will discuss in this chapter. Now, normally to know the relation between T and K, we work under the assumption of delta H and delta S are constant at any temperature. So if we take this equation over there, then we try to substitute the value, we will get that ln K1 is equal to minus delta H over R 1 over T1 plus delta S over R, and ln K2 is equal to minus delta H over R 1 over T2 plus delta S over R. And now we can just subtract this equation because we assume that delta H is the same for any temperature, and so does the delta S as well. They're also the same for any temperature. Therefore, delta S over R minus delta S over R will be equal to 0. Ln K1 minus ln K2 will be equal to ln K1 over K2, and this will be equal to delta H over R 1 over T2 minus 1 over T1. So in this case, we can find
the new K or K2 if we increase or decrease the temperature from T1 to T2, and the value will be dependent on the delta H, whether it's an exothermic reaction or endothermic reaction. Please note once more time that the only thing that will change the value of the K is indeed the only change of temperature. Even though the reactions could shift based on Le Chatelier's principle, still the only thing that could change the value of K is the change in temperature.